Bismillah ar-Rahman ar-Rahim. Let's solve this exercise 1 for the steady-state cascade model. We need to calculate the expected concentration of nitrate in 3 lakes in series. Let's plot lake number 1, lake number 2, and lake number 3. And we can see that the loading, of course, every lake has volume. They have loading, they have flow rate, and they have decay rate. So the loading of lake 1, I'm going to put it here, and I'm going to call this loading 1. Okay, and then we will have K, decay rate of this one, K1. And then this is the flow rate 1, 2. Flow rate going from lake 1 to lake 2. And this is the concentration leaving lake 1 is C1. Of course, this C1 is going to lake 2. And this lake has also another loading, a different loading, W2. Of course, you can see it. Lake 2 has 10 kilogram per day. And it has also a factor K. Let's call this one. We could call it, it seems to be that they're all 0.7, 0.7, 0.7. So it's going to be K2, which is equal to K1. Same thing here. Now here you will have a flow rate Q, lake 2 going to lake 3. And this is the concentration of lake 2 going to lake 3. It's not even treated in lake 3. And then lake 3 has a loading, W3. And then the degradation rate is K3. Again, K3 of lake 3 is 0.7, which is 0.7 per day, which is the same as K2, same as K1. And then leaving lake 3, going, for example, to irrigation, going to the ocean, going whatever, okay? This is Q3 to the lake number 4 or some other end results. We don't know where it's going at the end. Let's say Q34. And then this is the concentration of lake 3 going to the future lake or going to the future place. Okay? So let's try to analyze this and calculate the expected concentration of nitrate in 3 lakes in series. Okay, we have the volume, volume 1, which is 10 to the 6 meter cube. We have the volume, volume 2, 10 to the 6 meter cube. And we have the volume, volume 3, which is 10 to the 6 meter cube. Of course, we have the loading of each, 26 kilogram per day, 10 kilogram per day, and 15 kilogram per day. And we have the flow rate constant. So the flow rate from 1 all the way to 3 is 10 to the 6 meter cubic per day. Let's start right now doing the mass balance for lake number 1. Okay, so lake number 1, when you do the mass balance, it's volume 1 dC over dt, and this is the change of concentration in lake 1 with time, is equal the loading. Now this is lake 1. Remember, it has a volume, volume 1. It has K, which is the same as, we're gonna make K as fixed K, but we're gonna call it now, and unless one time that lakes has different Ks, so we have to specify is K1 similar to K2 or different? So here they are similar, but we should still put K1 as a factor. And now you can see here Q1 going to 2, and this is here C1. And of course, there is a loading. So if you do mass balance, V1 dC1 over dt is equal loading, which is input, minus Q12 times C1, and that is the loading of leaving the lake number 1, minus And then you have the reaction, volume 1, K1, C1. So we're assuming that these lakes are staying for thousands of years. So dC over dt is equal to 0. Okay? Which means if you rearrange the equation, loading 1 is equal K1 2 C1 plus V1 K1 C1. Which means this is the input. And all of this is the output. So if you want to find C1, just take C1 as a common factor. And it will give you this equation. C1 is equal load 1 over Q plus K V1. So the load 1 is 26 kilogram per day. The flow rate is 3 10 to the 6 meter cubic per day. K is 0.7 per day. 0.7 per day. And V1 is 12 10 to the 6 meter cube. You can see here meter cubic per day, meter cubic per day. You could see cancel day with day. You will end up with kilogram per meter cube. And this would give you 2.28 10 to the minus 6 kilogram per meter cube. So that is the first lake. So the concentration leaving lake number 1 is 2.28 10 to the minus 6. Of course, kilogram per meter cube is equivalent to microgram per liter. So it's going to be 2. This is kilogram per meter cube. So it's going to be almost, let's just leave it as 2.28 10 to the minus 6 kilogram per meter cube. If you do kilogram to gram, this is 1000. Gram microgram, this is 10 to the 6. Kilogram with kilogram, gram with gram, microgram per meter cube. And then you want to do it per liter, so meter cube per liter. You know that 1 meter cube is equal to 1000. So meter cube with meter cube, 1000 with 1000. You'll end up with, look at that, 10 to the 6 and 10 to the minus 6. The answer would be 2.28 microgram per liter. 2.28 microgram per liter, which is equal to 2.28 part per billion. So this is the concentration of nitrate leaving lake number 1. Let's go for lake number 2. We'll do the same exact solution. Let's go to lake number 2. Lake number 2, the flow rate entering lake number 2. If you just look at the previous slide, it's flow rate coming from lake 1 going to lake 2, and concentration 1 leaving lake 1 going to lake 2, and of course K2, which is equal to K1, and the loading W2, and the flow rate leaving 2 going to lake 3, and the concentration 2 leaving lake 2 to lake 3. So if you do a mass balance for this, you'll do the same thing. V2 dC2 with T is equal to, now you'll have two inputs. Imagine these two inputs, Q12, this is one input, times C1, plus W2 is an input, minus the output, QT3C2 minus volume 2 K2 C2. Of course, this is equal to 0. And you could rearrange the whole thing as equal to Q12 C1 plus load 2 equal Q23 C2 plus, there is no space here, V2 K2 C2. So, concentration leaving lake number 2 is equal load 2 plus, you can see it here, load 2 plus Q12 C1. So this is Q12 times C1. Okay, and this is divided by the flow rate, this flow rate, and that is flow rate 23 over, of course, this is C as a common factor, over K2 volume 2. And that's, if you plug in the numbers, you will get 1.95 10 to the minus 6, which is almost equal to 1.95 part per billion. Imagine what was the concentration before? 2.28 leaving lake 1. It will be 1.95 leaving lake 2. Now, let's do lake 3. We'll do the same exact thing for lake 3. So we'll do lake 3. Okay, so you'll have Q23 C2 entering lake 3. You'll have load 3, and you'll have Q34 leaving lake 3 to whatever after lake 3. Okay, times, C3 at the bottom. And you'll have the degradation rate of lake 3. If you have settling, you should add it with the degradation too. So you could check this. You could redo the modeling for this, which is going to be similar to the modeling of lake 2. So you'll end up with C3 leaving lake 3. It's W3 plus Q23 times C2 over Q34 plus K2, Q34 plus K3 V3. And that would give you an answer 1.54 10 to the minus 6 kilogram per meter cube, which is 1.54 part per billion. Okay, so this is the final answers. The concentration leaving lake 1 is 2.28 part per billion, and the concentration leaving lake 2 is 1.95 part per billion. Concentration leaving lake 3 is 1.54 part per billion. There's a little bit reduction every time it leaves a lake. Okay, we should always set up a mass balance for each lake, or we should just set up a control volume. We should solve it in series, compute C1, then use it to compute C2, and then C3. If the volumes or the loading differ between lakes, then you cannot use the simplified cascade shortcut. Instead, you must compute each lake individually. If there are multiple loads entering at different locations, trace these contributions through the system step by step, because you have to make it input minus output. And also because the cascade is no longer uniform, you have to make sure that everything is taken into consideration. Our consumptional illustration that if loads enter at different lakes, the system no longer behaves like a simple geometric cascade. Load from lake 1 goes treated and then goes to C2 and then goes to C3. Same thing, load at lake 2 gonna produce C2 and then give you C3. Same thing for load at lake 3 will give you concentration as C3. Each load must be carried forward. That's why it's called forward independently. And then it should be summed. The general approach, mass balance, then you should solve it and you should propagate downstream. Thank you.